Hello, everyone. Yeah, we're just about to get started. Just need to have Aaron up as a speaker or co-host. Waiting for him to come up. There we go. He's a speaker now. Hello, Aaron. Hello, Abad. Um, cool. I think we will get started and yeah, dive into the papers. Um, yeah. Okay. So let's get started. So the first paper to talk about um, is AI agents that matter. So let me pin that to the space. Just give me 1 second here. Um, cool. So this is a very interesting paper, I would say. This paper is it's more of like taking kind of a deep dive, introspective view as to the field of AI agents and what's going on, I guess, in that field. So yeah, they make several observations about the current state of AI agent research and development. So the first important observation they make is that when you have AI agents that they have like an environment that's easy to check the answer is correct or not. So for example, like if you're doing coding and you're checking test cases, you can like easily check. Okay, these are the if your solution matches the test case, solves the test cases, for example. Like then if you have situations like that, then you can just throw like a lot of inference compute at it and just increase accuracy. You can like just keep trying and trying again with your agent, and so, like, one thing that a lot of the studies so far haven't really taken into consideration when they're reporting their results is they don't report like the cost of the AI agent, because you could throw more inference compute at it. Of course, the cost would go up, but you would get better accuracy. So they started. This paper tries to visualize the accuracy cost trade off, and they have a Pareto curve sort of graph for this, and they plot a few of the. They look at specifically in this case, they're looking at human eval, so that's for coding, and they plot some of the state-of-the-art models there, looking from which they found on papers with code. So the state-of-the-art models that also have code. So they have they mentioned a few LDB, LATS, and Reflexion. So they have these ones that they looked at, and then they also have a few baselines. So they have like just GPT 3.5 and GPT 4 zero shot. They have like again like retrying the model if it doesn't work, if it doesn't pass the test cases, so you can retry it up to 5 times, or you can retry it but increase the temperature each time you retry it. So that increases stochasticity, and you have a you may have a better chance of getting something that works. So they call that a warm-up strategy. And then the last baseline they have is an escalation baseline, where basically you start out with a cheap model, so something like Llama 3.8b, and if that doesn't work, then you escalate to more and more expensive models until you reach like GPT-4, for example. So they have these different state-of-the-art agents and these different baselines. But what they've observed is that actually these sort of quote-unquote state-of-the-art agents don't actually outperform these simple baselines. And on top of that, the cost of these agents differ drastically. So, for example, they say for substantially similar accuracy, the cost can differ by almost 2 orders of magnitude. So in the one that I guess the baseline that they said worked quite well was this warm up baseline where you retry with a model like GPT-4, but you increase the temperature each time you retry. And just that simple approach is as good or even better than some of these quote unquote state of the art agents. And on top of that, like this is kind of showing that there's all these sorts of like system two approaches, as they call, which are supposed to be using things like planning and reflection and debugging. And people have been saying, oh, these methods are giving better performance, but there it doesn't actually seem to be that much evidence that these methods actually are better than baselines. It's just that people haven't really adequately tested the simple baselines. So that was an interesting result that they found. And then more importantly, they're advocating for basically, of course, keeping into account not just accuracy but other axis of metrics to keep in mind, mainly the cost, for example, and optimizing accordingly. So, for example, they have another sort of case study where they look at the hot pot QA task, which is a sort of multi-hop question answering. So it requires you to gather different pieces of information in order to finally create an answer from that. And so they have they are designing agents for this hot pot QA, and they use DSPy and Optuna, and they're trying to design it by searching for parameters for things like the temperature in the modules of the agent, number of few shot examples, selection of those examples, etc. And if you optimize for just accuracy, you may get agents that will perform well, but the cost may be quite high. But if you jointly optimize over the cost and accuracy, for example, what they did that with GPT 3.5 as the base model for their agent, this resulted in 53% lower cost for a similar accuracy to just optimizing for just accuracy. And similarly for Llama 370B, they got a 41% lower cost. So you have to also optimize not just for accuracy but also cost, so that's what they're trying to advocate for. On top of that, they're advocating for evaluation results that when you're displaying the evaluation, you should be able to display not just the accuracy but things like cost, or they have the option. The user should have the option to provide, of course, like the cost will depend per API that you use, and of course the cost changes. Maybe it'll get cheaper it gets cheaper over time, of course, so maybe these models will be it'll be cheaper. So you ideally you would for example, provide maybe instead of just the cost, maybe it's like the number of tokens that this model is using, and then you can calculate the cost yourself, or you can provide the API cost in the evaluation benchmark, and it will give you the cost for the number of tokens it's using. So they have an example sort of like web UI that they've linked to in the paper for something like this. But the point is when you do these sorts of things, your conclusions may be different. So for example, they look at this other task called novel QA, and this is another benchmark which is looking at question answering over long novels. So of course you could look at things like RAG, retrieval augmented generation, or you could also look at just using long context models and which one would be better. And what they've observed is if you look at just accuracy, you'll see that the approaches are roughly equally accurate. But if you also look at the cost, RAG will cost over 20 times less. And so if you actually look at the cost, maybe your conclusion is that actually RAG would be better if you're a model developer, or you're building some actual tools around this, that RAG might be better because you're getting similar accuracy but half the cost. So yes, these are things that people are not, I guess, considering from a research angle when you're publishing their benchmarks in research papers. So they kind of also argue that there may be different types of benchmarks needed for just research versus also more application and application-driven benchmarks, for example. Another problem that they've observed is a lot of these benchmarks don't have held-out test sets, which is very problematic, and sometimes those held-out test sets don't are quite similar to the training set, and so you can't really evaluate the generalizability of the agent. So they're saying if you're the more general the intended generality of the agent, the more the held out set should differ from the training set. So that's what they're advocating for. So again, they have an example here of like Web Arena, which is one of these agent benchmarks for you applying agents to navigating the web and navigating websites. And one of the top agents there on the benchmark for that task is it's called the STEP agent. But the STEP agent hard codes policies to solve specific tasks in the web arena. And this is fine for that paper because I guess their paper had a different goal. But overall, it can be quite misleading if you're looking at the web arena, and because the held out set isn't that general. It's just including the similar sort of tasks and similar sort of websites, and so it can be very misleading for developers who are looking at the leaderboard. So yeah, they're also pointing out that this can be quite problematic. And then also these benchmarks don't account for human in the loop. They're looking at mostly the tasks being performed without supervision, but actually having human in the loop may actually increase the accuracy of some of these models. So for example, they cited a paper where simple feedback improved the performance of GPT-4 on some challenging programming problems from 0% all the way up to 86%, just with a little bit of human feedback. So actually, if you incorporate human feedback, you may actually end up with very different results, and that the evaluations aren't really considering this so far. So overall, these are the various issues that they've pointed out, and again, they're also observing just, of course, a lot of problems in the standardization and reproducibility of a lot of these benchmarks as well. And so overall, they are advocating for a more standardized evaluation framework, just like how like typical LLM evals have, frameworks like LM eval harness or Helm. There should be some frameworks for a more standardized framework for agent evaluation. So that's what they're advocating for in this paper. So yeah, I think this is a good analysis of the evaluation of agents, and yeah, as they say, how to evaluate agents that actually matter and that have actual practical use cases. So I think it was quite an interesting paper.
Yeah, this is very interesting. Thanks for presenting this paper. I have a few comments and questions.
Yeah, sure.
So
yeah, go ahead.
Oh, sorry. Okay. So as for mixture of, so there was this recent paper, mixture of agents. They did definitely show this kind of, dollars versus performance graph. So it seems that there are some people who are starting to consider the cost. But, yeah, like you said, yeah, I didn't really see that graph in other papers. So, yeah, I hope this direction is going to take off.
Yeah. There were some questions here about how do you think we can get closer to more end-to-end agent architectures, which aren't handcrafted but learned? I guess the agent design is also related to the bidder lesson. Yeah, I mean, I agree with all of that. Like, I don't know. Yeah, I think a lot of these agents seem to be handcrafted. And yeah, it's not very bidder lesson pilled. So yeah, I do. I'm not sure, but how to get closer to these sort of end-to-end agent architectures. I don't know a whole lot about agents. I'm pretty new to this field, to be honest. But yeah, I agree that from what I've seen, a lot of them are very handcrafted and not bidder lesson pilled. So I would agree that would be something that needs to be worked on.
Yeah. So
yeah.
So as for step agent, yeah, I was reading that paper recently because that was probably one of the best open source models for web navigation. But yeah, I definitely saw like some handcrafted code, but not all web navigation papers uses hand coded approach. So I'd say it's there are some yeah, you probably have to pay a bit of attention, but yeah, not all of them has that problem.
Okay, cool. Are there any other comments or questions? If not, the next paper, or I guess topic to talk about. Oh yeah, go ahead.
Yeah.
Was there something?
As for lag, I think lag is definitely usually cheaper than just long context thing, but sometimes I guess it really depends on the approach. When you want to summarize like a whole book, you don't really want to use lag based approach, because lag based approach only retrieves like small number of pieces. On the other hand,
Right.
yeah, summary requires like a broad. You want to cover much broader coverage of the whole paper, a whole book. So yeah, I guess it depends on the task.
Yeah, I think the novel QA was like asking specific questions about about stuff happening in the novel. So then it's like it's not really a general summary, but like you have to go to the novel and find specific things. So I think for that task, that's why RAG would perform well for that sort of task. But yeah, I think if it maybe for more general questions, maybe something like a log context model, or not even like kind of like RAG, but yeah, like there were some of these papers that try to summarize different parts and then try to kind of aggregate them together. Yeah, but I think maybe it has more to do with this task specifically also. So yeah.
Makes sense.
Okay, if there are no other comments or questions about this paper, we'll move on to the next one, which I guess isn't really a paper, but it's the release of the Kyutai, I guess if that's how you pronounce it,
Yeah.
Kyutai Moshi announcement of that model. So I think Aaron was going to cover that.
Yeah. So, yeah, if you guys are interested in this, I'm sure it is very easy to find some like a demo tweet. So basically, this Moshi, so Kyutai Labs just announced free end-to-end audio model demo today. It's like a speech-to-speech system, so it can be thought of as an open source version of GPT-4o audio. The quality and timing is a bit less polished than GPT-4o at this moment, but will be improved. And so this web demo is also available. Many people are trying it right now. The model training pipeline and model architecture are very simple and very scalable. With that, only about 8 people team, and it was done in 4 months. Apparently, synthetic data was very big factor. So let me talk about architecture. It's a very simple 7B multimodal language model. So speech in, speech out, and two-channel I/O with streaming language model constantly generates text tokens as well as audio codecs. I think I know what kind of thing they do. So basically, there was this paper released by with one from Meta with many authors. One of them was became the lead of GPT-4o audio at OpenAI. According to that paper, they basically interleaved text, so interleaved audio tokens with the transcript of that component, and this audio token is, I think, Hubert tokens in that paper. So yeah, this approach apparently was the best approach, and Hubert tokens was also kind of like compressed. So you don't have to, if I understand correctly, you don't have to generate 50 tokens per second or something like that, which would be super slow in latency. So yeah, so they achieve 160 millisecond latency, which is much better than GPT-4o, which was like 250 millisecond. Maybe because GPT-4 is much bigger than this one, and this it has real-time factor of 2, and the base text language model is 7B trained from scratch. It's called Helium 7B, So Helium 7B is then jointly trained with text and audio codecs. Speech codec is based on Mimi. Apparently, it's their in-house audio compression model. Mimi is a VKVAE model capable of 300 times compression factor, trained on both semantic and acoustic information. 300 times, I wonder how many tokens they're going to have per second in this case. If you have like a 44,000 steps per second, then that's going to be like maybe about 100 tokens per second, maybe. That's much bigger than the aforementioned approach, but I guess it's still doable with 7B model. So their TTS engine supports 70 different emotions and styles, like whispering, accents, personas, and so on. And now let me talk about training and LLaRA they used. Their model is fine-tuned on 100,000 transcripts generated by Helium itself. So yeah, this is where the synthetic data comes in. These transcripts are highly detailed, heavily annotated with emotion and style and conversation. And their TTS engine is further fine-tuned on 20 hours of audio recorded by some voice actor. So yeah, the model can then be fine-tuned with less than 30 minutes of audio. Their generated audio is watermarked, and generated audios are indexed in the database. Apparently, it was trained on their cluster called Scaleway with 1,000 H100 GPUs. Inference, their deployed demo model is capable of byte size of 2 with 24 gigabyte VRAM. Model is capable of 4-bit and 8-bit computation. It works across backends like CUDA, Metal, and CPU. And inference code is optimized with Rust, and it can be further improved. It was further improved with better KB caching, prompt caching, and so on. For the features, they're trying to release technical report and open model release. And open model releases would include the inference code base, the 7B model, the audio codec, and the who optimized stack. And so they're trying to scale the model, refine based on feedback. And license is going to be permissive, but actually it's yet to be decided. But yeah, they're definitely going to open source to some extent. In my opinion, open source, high quality, low latency, embeddable speech-to-speech systems can have another stable diffusion moment. In this case, the impact can be even greater than stable diffusion, given the greater generality of language models. But there will be many more high quality open source speech-to-speech models released after this, given that there's so much competition. So I don't think Kyutai is going to be like the only player in this. Do you guys have any comments and questions?
Yeah. So, before I ask my question or clarify, I wanted to clarify. I was just going to mention, if anyone has any comments or questions, feel free to reply to the space with their comments and questions. Yeah. So I guess so. I'm just trying to better understand this. So they have a multimodal model, and it's taking in, I guess, speech tokens. But then it's also taking in text, or like it's processing text as well. How does that? Because it has the I guess it has text tokens as well, and then it's outputting then speech tokens at the end. Yeah, I guess it was a little bit unsure about that.
Yeah, so the details, actually, I'm not really sure, but it appears that they are interleaving text with corresponding audio tokens. So basically,
I see. Okay.
first they generate text and then generate the corresponding audio parts.
I see. Okay. Okay.
Apparently, that seems to be like a common practice for some of the latest speech-to-speech system. There was like a paper released in end of last year, which basically concluded this approach is better than other approaches.
Okay. And so then technically you should also get then you'll have the generated speech, but then you should also have you have the text transcript produced as well for that speech, correct?
Yeah.
Okay. And then were there any details released on how the text-to-speech engine works?
Basically,
So I guess because you have like you'll have the speech tokens that are I guess it would just be part of the VQVAE because you have the speech tokens that are produced and then that just gets passed into the VQVAE and then that somehow will generate the speech from there, or how does exactly that work?
So yeah, speech part is discretized into discrete tokens with VQVAE. It seems like it has 100 tokens per second, and that's like a standard VQVAE. So basically, there are many speech models using VQVAE for audio discretization, and that's like typically. So yeah, and in this case, so in the paper I was talking about, they used Hubert for tokenization, but apparently they used VQVAE for this one. Sorry, does that answer your question?
I think so, yeah. Okay, yeah, that sounds interesting. Yeah, looking forward to it getting open sourced.
Yeah, so
let's see, is there
apparently they're also focusing on like embedded applications. 7B is small enough for such applications, even though this is not. The thing is, GPT-4o audio has 250 millisecond, even as cloud cloud version. So I don't think this has to be embedded. The latency is not too bad, even as cloud. So yeah, if you really want embedded, then yeah, that works too. So
yeah, that's cool. Yeah, if there are no other questions, then we'll move on to the next paper. The next paper is, let me see here, Meta 3D Gen. I will try to pin that as well. This is a model that is announced by Meta. They have actually 3 papers dedicated to this, and we'll see why. Yeah, this is basically a sort of text to 3D generation pipeline that they have, and you can see the results are actually quite good, quite high resolution. And it can do all this generation in less than a minute, so it's quite fast as well compared to some of the other state-of-the-art techniques. The way that they do this is that they have a 2-stage pipeline, and so they actually have 2 models that they've trained. They have one called Acid Gen and one called Texture Gen. And they're actually separate papers for the Acid Gen and Texture Gen, and then of course the main paper for the Meta 3D Gen. So there's actually 3 papers in total about this. So the Acid Gen is a text to 3D generation model, and so that one takes in text and it will generate a 3D mesh, and it will generate also associated textures for that as well. But the problem is those textures aren't oftentimes not very high quality, high resolution. So they have a separate model called Texture Gen, which can also be used separately, which basically, given some sort of mesh, whether or not it's generated, or it could also be an artist created mesh, then it will retexture it, or apply some texture to it, based on a text prompt. So basically, if you want to do from scratch, your two-stage pipeline would be you pass it into the acid gen, and then from the acid gen, you pass it into the texture gen and generate the final refined uh, uh, 3D object with with these refined textures generated by texture gen. So yeah, basically the way these models work is like they're based on text image generators. They're actually built on top of the EMU model that Meta has previously developed, and they are generating they generate different views from the text image generator is generating different views of the 3D object. That's what it's trained to do, and it's trained on renders of synthetic 3D data. And so yeah, the model is trained to generate fairly consistent views of the object, and then it will also generate an initial version of the texture, and then the that result is passed into texture gen, which regenerates the texture given the mesh that was originally generated by the asset gen model. Yeah, and then there are more details, of course, in the individual papers about asset gen and texture gen. But yeah, in general, like they've evaluated the results across different metrics like prompt adherence and visual quality, and they've evaluated it both with laymen, just random people who are qualitatively they're looking at it and rating it, but then they also provide it to professional 3D artists and also ask them to rate their results. And in both cases, they've observed that their results are beating many of the existing tools that are out there, like even some of the products as well that are out there. And yeah, so they've done this sort of quantitative human evaluation, and then of course they have a whole bunch of qualitative results where you can see the quality of the generation. And I guess you can see some of the results in the video that I've pinned to the top of the space as well. But yeah, I mean, I think this is certainly quite impressive. The other part, it's not just about providing high quality results, which it's able to do, but it's also able to do this quite fast in less than a minute. So that's another huge benefit. I guess part of it is, yeah, it's like, yeah, I guess it's, yeah, I think overall, yeah, I think it's a good step in the right direction. And yeah, unfortunately, it's not open source. That's the unfortunate part. I don't know if they do. I don't know if they plan to open source it anytime soon. I mean, maybe they probably are gonna, make it part of their products in some way. Part of their maybe it's part of their metaverse direction. Maybe. It's. I mean, it was built on top of the EMU models, and the EMU models also weren't open sourced. So yeah, I'm not. I think yeah, that's one unfortunate part, but at least they're pretty detailed research papers explaining what they did, so that's quite nice. Yeah, are there any questions or comments about the Meta 3D Gen paper?
Yeah, I don't think they're gonna open source it, given they wanna make money from metaverse,
Yeah,
but hopefully
yeah,
this is gonna motivate other people to open source higher quality 3D models, because and all these models objects generated look super clean and high quality compared with anything else we see. So uh, yeah, I don't think it's
right.
hard to build better open source models. So yeah.
Yeah, I agree. If there are no other comments, let's see. Yeah, nothing else. Um, then yeah, we'll move on to the next paper, which is Open Television. Um, yeah,
Yeah.
I think Aaron, that's you're going to cover that.
Okay. So give me a moment. So Open Television basically lets you immersively operate a robot even if you are 3,000 miles away with negligible delay, so like a 60 hertz. So it can just do like a without any noticeable delay with 60 hertz, which is impressive. This allows easier collection of on-robot data via remote teleoperation, and the system is open sourced. So yeah, let me give you more details. So it uses VR devices to stream the hand, head, and wrist poses to the server. The server retargets the human pose to the robot and sends joint positions targets to the robot. They train an imitation policy for each task with an action chunking transformer. The transformer encoder captures the relationship of image and proprioception tokens, and the transformer decoder outputs action sequences of a certain chunk size. So let me give you more details on the system. The VR devices stream the operator's hand, head, and wrist poses in SE3 to the server, which handles the human-to-robot motion retargeting. In turn, the robot streams stereo video at a resolution of 480 times 640 for each eye. The entire loop happens at 60 Hz. While their system is agnostic to VR device model, they chose Apple Vision Pro as their VR device platform in this paper. So they validate the effectiveness of their system by collecting data and training imitation learning policies on 4 long horizon precise tasks, including can sorting, can insertion, folding, and unloading for 2 different humanoid robots and deploy them in the real world. The trained model achieved great accuracy using stereo input, and Dino version 2 over ResNet 18 led to notable improvement. So yeah, this paper, unfortunately, is I don't have much. There's much things to talk about it, but I think this has huge implications. Okay, so a collection of robotic trajectories is often conducted via teleoperations nowadays. A large-scale collection of diverse trajectories is very, very expensive, especially if it has to be performed locally. It would require to employ many people for many hours and require physical presence of workers at where the robot is located. So like yeah, I would imagine you have to collect millions of diverse data collected, and unlike data collection for GPT-4 and other virtual model, you have to bring all these human workers to the site. So I'm sure it's easy to transport robots, but the transportation cost of these human workers is not negligible. So this remote operation would not require physical presence and makes it easier to hire more people without transportation cost. So it allows hiring many people from traditionally poorly paid areas, even foreign outsourcing. But obviously, if you go beyond 3,000 miles, like across different countries, I'm sure the latency from internet connection is going to be not negligible. So probably has to happen, and maybe it can go beyond Mexico. It can go to Mexico, but probably not can go to Africa, let's say. So also this allows physical labor to be remote work. So yeah, it will probably take like 10 years until robots taking over most of the human jobs. Until then, I'm sure there has to be some humans have to intervene. In which case, this remote teleoperation operation is going to be very useful. So yeah, do you guys have any comment, question?
No, I don't have anything. I think that looks interesting. I don't know if it doesn't seem like anyone else has any comments. Yeah, yeah, I mean, it seems like yeah, it would be very useful for collecting data and makes it easier for people who collect these robot
So
trajectories. So yeah, that's very interesting.
yeah, actually, I don't know much about like a remote teleoperation for like a remote physical labor jobs. I wonder if there's jobs like that right now. Oh, you know, we we sometimes hear like doctors controlling a surgery robot or something, but it happens in very close distance to the robot. So
Right.
yeah, that
Yeah.
should be a thing right now because it doesn't. Oh yeah, obviously, UAV controlling UAV can be considered like that, but I'm sure there are more possibilities.
Yeah. I mean, I guess the question is like latency in terms of like things like internet connection and stuff like this. That could be a problem. Um, that's something definitely to keep in mind, I guess. If um, I don't know, maybe for like maybe just for generally collecting data, that's not as much of a problem. But for something like surgical robotics, obviously there would be a huge problem. So I don't know. That's something I don't know if they've analyzed that very carefully. If you know what the latency is like, you know how that's affected, and um, I guess they talk about everything happening within 60 hertz, but I don't know. That's under certain assumptions for the things like internet connection. I'm not sure what that how that is determined.
Yeah, that's true. Um, yeah, this could be even be a viable startup idea. Depending on latency. So,
Yeah, depending on the latency, yeah.
so if you guys have any idea, let us know.
Cool. Okay, the next paper is PathAlign. Okay, let me pin that to the space as well before I get started here. Okay. So, okay, so this is a paper that is released by Google. It's a medical AI paper, so kind of I found it a little bit interesting. I just wanted to quickly talk about it. Okay, so this is a paper looking at training a vision language model for whole slide images in pathology, in histopathology. So just to provide a bit of background, like typically you'll have like in medicine, you may have like, for example, biopsies. Those biopsies, are used for diagnosis of, say, like for example, of cancer. The way it's done is that you have those tissue, that tissue is put on a slide and is examined under the microscope by a pathologist. And so people have been now interested in how to use AI to analyze these slides. And so yeah, if to uh, so people have been developing AI methods for this. One of the challenges of dealing with these sorts of slides, and I guess when you're doing them digitally and with AI, you're working with whole slide images. So those, you have the actual images of the slide, but these images of the slide, you're doing it, at high magnification. The images can be very big. They can be like gigapixel level images. So there's a very huge images, that you're looking at the entire the tissue, and then you'll have details at like at the cellular resolution, for example. And when you're looking at a whole slide, that can be you're looking at a very small part of the maybe there's some details at very small part of the entire gigapixel level image. So, the past people have been developing foundation models for pathology. A lot of those foundation models are at the patch level. So what people do is they take patches from this whole slide image, this gigapixel size image, and they train models on top of those patches. And so you'll have, you may have like hundreds of patches or even thousands of patches per image. But you're not looking at the whole image together. You're just looking at the patches. And so people have been training models for that, training, for example, a vision transformer on that, or people have been training multimodal models on this, for example, as well. But that's, you want to look at the full picture. You also want to look at the whole slide image. So there have been a couple papers that have looked at training foundation models for whole slide images as well, but of course it's a much more difficult problem. On top of that, there haven't been a whole lot that try to train sort of these multimodal models where you're aligning the image representation of the whole slide images with corresponding text. So there haven't been a lot of papers looking at that. And so this paper from Google, that's what they're trying to address, is trying to train a foundation model that has that is like a vision language model, but specifically for these gigapixel size whole slide images. So the way they do that is that they're using an approach. The multimodal approach that they're using is this BLIP2 framework. And so they have what they're doing is that they actually have they do have a patch level foundation model. So they actually start out with a patch level foundation model that is taking in the patches from the whole slide image, and it is producing embeddings. So this is just like a self-supervised learning model that has been trained separately, and it's producing embeddings for the patches. But then those embeddings for the patches can be passed into this BLIP2 model, so you will have a sequence of these patch embeddings. So they actually have a sequence of 10,240 patch embeddings, per whole slide image that you're analyzing. So you have these sequence of patch embeddings that are passed in to this BLIP2 framework. You have this sort of whole slide image encoder. And then that's trained jointly with the text encoder according to this BLIP2 framework. And so you'll have a corresponding text encoder. So that text encoder is getting in input from it's getting in input from the input would be like the pathology report or something is what it'd be trained with, like the pathology report, or there'll be like maybe questions about the whole slide image, and so the text encoder is getting that data as well. And then you can train it. So if you want to do like things like you can originally train it to do things like retrieval. So you can, like, for example, retrieve, like if you have like a whole slide image, you can retrieve text that corresponds to that whole slide image, like for example a diagnosis or something like this. Or what they also do is you can also like connect it to a language model, a generative language model. And so they use, for example, because they're at Google, so they use PaLM2. So they have a PaLM2 small, and so they connect it to PaLM2 small. And you can just have you have like a simple linear layer connector. You can connect it to that model, and you can further fine tune it for text generation. And so you can do things like retrieval, classification, also now text generation, all at the whole slide level rather than at a patch level, which was what most of the previous papers were doing in the past. So that's kind of what they showed, and of course they compared to there were a couple papers that they compared to as well, in some previous literature they compared to, and they were observing better results for things like retrieval and classification. But also it's a little bit hard to compare because of all the data splits, and for example, some papers like they trained on, for example, one of the data sets, which is the TCGA data set, while other papers used it as a test set. So it's a little bit hard to do a proper comparison. But they were showing some promising results. The LLM results were also promising, but they did observe there was some confabulations and hallucinations. But this is just like I think a kind of more of a preliminary work, and there's more work that can be done. I think it's an interesting kind of work in this space of AI pathology, and most importantly for trying to develop this sort of multimodal model for whole slide images, which is much harder than there's a lot of additional challenges when working with these gigapixel size images than when you're working at the patch level. So that I think is quite interesting. Let's see. Were there any questions? Let's see. Let's see. Okay, I think. Okay, Parm had some questions. No? Okay. I don't know what happened. What happened there?
So is this applicable to other gigapixel level images like satellite image and like astronomy type images?
I mean, theoretically, yeah. Or like, I think another example of a domain that people do this is like maybe with like satellite images too, as well. I mean, yeah, I think the approach would probably be applicable. Yeah, you could do the same thing where you train some sort of like patch level self-supervised model. Then you have you have the patch level embeddings that are passed into this sort of transformer for this blip2 model. Yeah, I think that whole approach would probably work well for other sorts of gigapixel level images and trying to train sort of vision language models for that. Yeah, I would agree that it would work. Yeah.
Do you know any like other applications other than the ones I listed? Like there's like a whole field of using this kind of models for like a histopathology, and could it be applicable to those areas? But I just cannot come up with any nice domain.
I didn't understand your question. What were you trying to say?
Oh, sorry. Is there any other gigapixel image domains other than this one, satellite images and that?
Yeah, I'm not sure. Those are the main ones that come to mind, like satellite images, I guess astronomy images. I don't know what else. Yeah,
Okay. Oh,
not sure.
Pam seems like she wanna talk. So
Yeah,
Hello, can you hear me?
yeah.
Um, Hi, Dinesh and Aaron. That was great. I was reading this paper literally yesterday. I noticed that they used these synthetic labels for the TCGA data, and that's the sort of main thing that I had questions about. Because I'm just wondering, so the use of these synthetic captions for the diagnostics, I'm wondering what you think about how that could sort of like, include potential biases, right? In it, in terms of like, it, just in, obviously in terms of the results, but also like how the model performance is affected. Um, yeah, I was just wondering what you think about that.
Yeah, I'm not 100% sure. So with the synthetic labels, they're using it for TCGA. So I think it's because they're talking about like I guess they have this part level labels versus the case level label, and in this case they only have case level information for TCGA, right? I think that was what their problem was. And yeah, I guess you know in a lot of times for like like these pathology things, like this kind of reminds me of also like a lot of times they also make assumptions when they do like the patch level models that the label is the same as the whole case level or the slide level label, which is not necessarily always correct, and it's quite noisy, but they're still able to learn meaningful representations from that. But it's not as good as if you had the actual like patch level data. So I mean, I'd say like you're yeah, I mean clearly you can learn something meaningful, but it's not as good as if you had the actual labels for the more fine grained labels. But yeah, I don't know about like biases and things like this. I mean, also the TCGA is not the largest part of the data set. They're using they're using a kind of a private data set of let's say there's like, what did I say, 354,000 whole slide images is in from this private data set, de-identified data from a teaching hospital, whereas TCGA has 12,000 whole slide images. So the TCGA isn't like is only like a small part of it as well. And I don't know if they probably, I don't know if they did those experiments. If so, I missed it, but they probably should have done some sort of ablation with and without TCGA. That would be interesting to see. I don't know if they actually did that. Don't think they saw anything like that.
I guess like I was very confused about why I guess like they did that myself, because like it seems like it's a relatively small fraction, but then like the reason why I kind of wanted to ask this is because I know you have extensive experience with pathology data in general, and I was wondering if this is like an actual common practice to do synthetic captions when you're training these models.
Yeah, I mean, for like medical tasks, like oftentimes, like, or especially like like there are various ways people have been generating synthetic captions. So like for like like I said, if you're doing for pathology, if you're doing things at the patch level and you don't have patch level labels, you will just assume that it's that the label is just the same as the whole slide image. Or sometimes if you're doing things like trying to generate, train image text models, and you don't have you have like just a data set of class labels, then you will generate labels. You will generate like captions based on the class label. Like, for example, oh, this image has this disease or something like that. You'll generate some sort of synthetic caption, even if it's just like a regular classification data set. So people have also done that. So yeah, people have been generating synthetic captions. This is pretty sort of standard so far in the field. I think if you are if you have other diverse data in your data set as well, then it's not as much of a problem. But if you're only training on these sorts of synthetic data, maybe it can be problematic. But yeah, it is somewhat standard that people have been doing these sorts of things before.
Okay, cool. That makes sense. Thank you. Like I'll hop off to listening. Just that was my main question.
Cool. Let's see. Are there any other questions? Doesn't seem so. Okay, if there are no other questions, we will move on to what is the next paper? Next paper is LLaRA. I think that's Aaron is going to cover that.
Yeah. So LLaRA basically creates a framework to turn robot expert trajectories into conversation-style data and other auxiliary data for instruction tuning. They achieved 10 times better sample efficiency over the baseline, which is RT2. So OpenVLA, RT2, and so on, they achieve great performance on the robotic manipulation tasks by turning the task into a sequence of vision language model tasks with vision language model architecture where the vision embeddings of each input frame are fed to the LLM along with instructions and actions. So the question is, can we improve the sample efficiency further by converting the visual information into text along with bounding box coordinates, which should be easier for large language model to understand spatial-temporal relations than from raw pixels? So yeah, that's the question. And this paper, they address that. Actually, I think this was also addressed by like some of the web agent papers. But anyway, this is like the robot version of it. So yeah, here's the method they used. So first, they transformed a typical behavior cloning dataset into an instruction tuning dataset. and fine-tune a vision language model, in this case, LLaRA, on this dataset. And the resulting LLaRA framework benefits from the broad inherent knowledge embedded within the vision language model, which enables better viscomotor task learning. Then they create auxiliary robotics instruction tuning datasets from the same source to enhance the VLM policy. The idea is that the auxiliary datasets will drive VLMs to learn better spatiotemporal understanding of the scene and eventually benefit robot learning. So their auxiliary datasets were constructed from the same robot expert trajectories. So yeah, they didn't use anything new. So the process depends only on object detection and runs in a self-supervised fashion without taking advantage of any external data. They learn multiple types of real-world robot experiments and found that their method, trained on only 8,000 simulated data, performs strongly in unseen real-world settings. With minimal in-domain fine-tuning, the model achieves 91.6% average success rate. So yeah, this paper is very simple in idea. They just used like a bounding box coordinates from which was detected using their model. Then they just added it into their instruction data for the model to be able to see those objects better. Because if you use raw pixel data, it doesn't really capture those information well. So basically, this lack of visual grounding is observed from various state-of-the-art vision language models, which should be a part of the reason why the proposed method is so effective. This inability also leads to suboptimal performance on various other vision-based agentic tasks like web agent. For example, GPT-4o is very good at OCR, but not good at bounding box coordinate generation of each text element. One way to improve visual grounding is to add more pre-training and fine-tuning data for visual grounding tasks. This does not even require any agentic data, so I guess improvement on these, probably those data can be synthetically generated using like OCR and so on. So yeah, once we have better visually grounded models, I think the sample efficiency of these models are gonna improve much better. Maybe not even without. It may not even need the proposed method in this paper, but I'm actually not super sure. Yeah, that's about it. Do you guys have any comments?
So yeah, I guess yeah, I'm curious how this compares to like some of the other methods which we've discussed in the past, like Octo, and I think there was like, was it OpenVLA? I think we've discussed some of these methods before. And do they compare performance to these things, or is that, or yeah, and then also maybe could these other methods also be improved by a similar approach of like, yeah, because they're just adding in some of the bounding box information into the data set as well, right? So into the model, they're passing in bounding box information, right? So have they tried, could that be tried with other methods as well?
Actually, so according to OpenVLA paper, Octo performs worse than LT2 or OpenVLA because their model was not robust to a bunch of other tasks. So
okay.
Octo is not really good. And also, actually, Octo, OpenVLA, and LT2 does not use bounding box information. I don't know, but so yeah, and LT2 and OpenVLA performs just as well. So we can assume that OpenVLA is probably performs as good as LT2 in this case as well. Mm-hmm. So yeah, given that this model outperforms LT2, yeah. So I think this one.
Okay.
So this basically this approach is orthogonal to OpenVLA. So yeah, you can just combine it with OpenVLA.
Okay, that sounds interesting. Cool. Are there any questions? Do people have any questions about this?
Yeah, by the way, maybe I already said this, but if you use bounding box coordinate information in web agent tasks, and they also see similar improvement. So
yeah, I think you mentioned that, but yeah, that's interesting. Yeah, like you said, I guess these VLMs aren't very good with like actually kind of the position of these objects and things like that. It's not very good with that. So yeah, that's interesting. Cool. If there are no other questions, doesn't seem like it. Yeah, if there are no other questions, we will move on to the last paper, which I will cover, which is consistency flow matching. Consistency flow matching. Let's see here. So I'm just going to pin that to the top of the space. This is a paper. Yeah. So this is a paper from yesterday. Yesterday, like, I don't know what it is. Archive. It's still like not working, but like the papers were like published, but okay, I guess it's now there. The papers are published, but before we couldn't see the list of the papers. So, but like it was some of the papers were posted on like the Hugging Face papers section. So I did find this paper over there, which is interesting. Yeah, I don't know why there was a problem with archive, but anyway, I'll talk about this consistency flow matching paper, which is a paper that was published by I guess the group of researchers in Peking University, but also in collaboration with Chenling Meng and Stefano Erman, who are also like really amazing diffusion model researchers. So yeah, this paper is like, I was kind of interested. But basically this paper is like trying to combine consistency models with flow matching and rectified flows. And so, the basic idea is that, consistency models have constraints on like, okay, you're generating at, so yeah, just to take a step back, I guess, you have like, diffusion models, which, they are iteratively denoising an image. So like you have a noisy image and you're trying to get to the clean image and you try to predict what the less clean image, the less noisy image would be, and you try to keep predicting what the less noisy image would be until you reach the final clean image. Then with consistency models, the way they are, the idea with consistency models is that they're trained so that you can pass in any noisy image and it's supposed to predict correctly the final clean image. So it's this idea of like it's consistent across any noise level that it's predicting the correct final clean image. So the way it's trained is like the loss function is basically that you have consistency between what your prediction is at a low noise level versus what your prediction is at a high noise level, and that they should both be predicting the clean image at the end. And so there's a consistency loss in there. And then you have things like rectified flow or flow matching, where you have this sort of like notion of velocity, where it's like, okay, you have you start at some noisy image or some noisy data point, and then you're supposed to go directly again to the final clean image, and so that gives you some sort of like velocity of like, this is the direction you need to go in to get there, and you have to learn that velocity at any point. So you learn some sort of velocity function at any point to get from a noisy image directly to the clean image. So it's actually more similar to like diffusion models, and it's very closely related to diffusion models. But the idea here now is like, could we also have a constraint on this velocity function? And they also have added a sort of a velocity consistency constraint as well. And they incorporate that with the consistency model. So they have, you have your regular consistency model constraint on, where you start at any point, they have to reach the same final image, and they have to be consistent. They have to produce the same image despite the noise level, whatever noise level you are at. But then also your velocity function will be the same at any point. And so they have a consistency for the velocity function. So, the velocity at the low noise level should be the same as the velocity at the high noise level, and you have a loss for that as well. So they have two constraints, the regular consistency constraint and then the velocity consistency. And this is what they train with. And on top of that, they also do multi-segment training. So you actually can divide the time into different you can divide your time from 0 to 1. You can divide it into different segments. And the idea is like if you didn't divide it, you'd have like you try to have extremely straight sort of trajectory from your noise to your final image. But then when you have this sort of different segments, you have like a piecewise linear sort of like trajectory from you have noise to some less noise, and that would be kind of a straight line going from the noise to less noise. And you have another one that's going from less noise to the final image. That's another straight line, but it doesn't have there's a little bit of more flexibility there. So it provides more flexibility for the model to kind of learn the trajectories and reach the final point. But of course that comes at the cost of like the nice thing about having straight trajectories is that you can do one step inference. You can go from it's a straight line that you just go and you can do just follow that straight line. And so that makes it easy to do like one step inference. But then with this multi-segment thing, you have to basically have as many steps as the number of segments that you have. So there's that aspect. And then on top of that, you can still do multiple sampling steps if you want on top of that as well. If you want to, I guess their claim is that will give you better sample quality and it will give you better sample quality if you do even more steps. But yeah, this is kind of the general idea of this paper. You can also technically do distillation, but they didn't test that, so we don't know how well the distillation works. But then they also have they do results with CFAR10, and that has like a standard UNet architecture. They show that it beats consistency models and rectified flows. But I must say the rectified flow results are very suspicious to me, at least. They do just the one step rectified flow, whereas they're comparing their model has like 2 steps, or I think theirs was like they were doing 2 steps or maybe a little bit more. So I don't think it's a fair comparison. And on top of that, I don't think it's a very well trained rectified flow. So I'm not sure if it's a fair comparison with the rectified flow. But the consistency model also, the consistency model too, like I think it's unclear if they're using like the latest there's like all this improved consistency training and all these additional tricks that have improved the quality of the consistency models. So again, I don't know if the comparison is necessarily fair there. But yeah, whatever it is, they are beating some of these models. They're also beating some of the diffusion models, but they don't beat some of the latest state-of-the-art models like EDM. I mean, EDM is not even that new. It's like from 2022. So it's also like, even then it's like, so yeah, it's still like, it's not, I guess, it's not state-of-the-art, but it's, I guess, it's decent quality, I guess. And then they also do high resolution generation. So that by high resolution, they mean 256 by 256 on animal faces, cat and celeb A HQ. And they only really compare to rectified flow again. I think the model this time maybe is a little bit better trained model, but that's all they compare to with the rectified flow, and they beat that. So yeah, I mean, this paper is interesting, and I think it's got some interesting ideas of combining consistency models with flow matching, and is worth exploring. But I think the results of the paper are a little bit underwhelming and a little bit unconvincing as to whether or not it is a better approach. So hopefully there are better follow-up papers that kind of study this in more detail. But yeah, I think it's an interesting combination of consistency models and flow matching. So yeah.
Sorry, did they use any dataset larger than CIFAR10, AFHQ, CAT, and Celeb AHQ?
Yeah, that's the large data set. It's just like this 256 by 256 images from AFHQ, CAT, and Celeb AHQ.
Okay.
So that's all they have. And I think it sounds like they want to do more. So they talked about future work being for example, text to image generation and things like this, but that they haven't analyzed that in this paper yet. So yeah.
Okay, interesting. Yeah, generally speaking, those data sets are a bit too small to make any conclusions about the model.
Yeah.
Like, it has to be like a ImageNet. Then yeah, it's probably like a good data set for.
Yeah, they didn't do ImageNet. Yeah, that would be good if they had those results, but they didn't do ImageNet. Yeah. Yeah. Cool. Yeah, thanks for pointing that out. Let's see if there are any other questions. Doesn't seem like there are any other questions. So in that case, Aaron, is there anything else you want to point out or cover?
Oh, you know what? I think we should cover that OpenAI's code verification model, but we forgot to.
Okay. We could do that next week too. That's fine, I think.
Oh yeah, I wonder if it comes with like a paper. Maybe not. Yeah, if so, we can.
I think it does. It does. The LLM critic one, right?
Yeah, because verification is super important, like especially for agent. So the problem with current agent models is that each. So let's say step level accuracy is like 95% or something, which is super high. But if you have 5% of probability of error at each step, then the overall accuracy drops exponentially to zero after like a small number of steps. But if you have a verifier like that, then and you can use some step level LLHF or like a process reward model, and you can basically improve the overall long range accuracy significantly, which apparently seems to be something that some like new startups like Zeta Labs is doing. And so that's something I'm very interested in.
Okay, yeah, let's cover. Yeah, I guess we totally forgot about it. We'll try to cover it next week. Then I think that would be good to cover. Cool. Yeah, I think that should be it if there's nothing else to talk about. But yeah, I guess thank you everyone for joining. I think we had a good turnout today and appreciate everyone joining us today. And we'll talk to you all next week.
Oh, Tanish, are we gonna keep this time at 1 p.m. PST?
I think this time, it's better for me at least. So I think maybe this might be, we might try to keep this time probably.
Okay, sounds good. Yeah, I can do that too. So okay, so see you guys next week.
Yep, see you all next week then. Bye.